All right. Well, welcome everybody. Let's see. Now I can't. There we go. Now I can't draw. Okay, so welcome everybody to our first module. You guys have been doing really great getting the homework in. I was talking a little bit before class and talking a little bit about the due dates. While this is not a normal class, so if you're a little bit late on things, or you turn them in early or whatever, or you're late, there's no marking you down for being late. So just get it turned in. And if by chance you get really, really, really busy and you can't do your work for that week, don't worry about it. Skip that week and do the week that we're working on. Okay? Skip that week and do the work that we're working on. And then when you have time, go back and fill it in. If you try and catch up, it's very, very frustrating and you won't be it'll be very difficult to do. So if you miss a week or two or whatever, just do the week we're on. All right. Does that make sense? And then you can go back at the end of the class. I usually put an end date on the classes, but I'm usually very flexible about that as well. So just know that you'll have extra time at the end of the class to finish off anything that you weren't able to do. So, all righty. So this week is module 2, food chemistry. I did put a link in here. It is kind of a nice link to an organic chemistry site if you're fascinated and you want more. From the discussion, there were several people that commented on functional groups, so I'll spend some extra time there. And somebody asked, I think in the last class, can atoms pick up more electrons to create a new shell? No, I don't, not in our world. Maybe in the real world of chemistry, but not in our little limited world of chemistry. We'll just take that as a no, right? We do have a couple of new students. Tracy, can you come on? Can you tell us where are you located and what's your company?
Hi, everyone. I'm Tracy, and I'm coming from Santa Barbara, California. Um, as it pertains to food science, most recently I was the head chef and culinary manager for Patagonia headquarters and developing products like tinned fish and spice blends. But I'm a chef by trade and currently a chef on a music concert tour. We're on a break for the next year or so, so looking to upskill and create more work in the food science realm. I do some consulting with smaller R&D brands.
Well, Tracy, what an interesting career. Who knew? I didn't know that touring bands brought their own chef with them. So, can we ask what band?
Yeah, it's a band called Coldplay.
Coldplay. Okay. Yeah. Oh, there's several nods from the younger people on the call. Very good. Yes, we're impressed. Okay, Andrew, where are you from? Andrew, you're muted.
Sorry about that. Uh, and I'll get on camera here in a little bit. I'm just dropping my son off at football practice, but I am in Iowa, so just right outside capital of Des Moines. I work for Casey's General Stores, so we're the third largest C-store chain in the country. Happen to be the fifth largest pizza chain as well, which a lot of people don't know about. So each of our locations are making pizza dough in house every day. So have the culinary background. Um, I've got a team of five with a lot of R&D folks, and I just thought this would be a great opportunity to learn more about the science side of it, so I can speak more of their language, if you will. So, looking forward to learning more.
Perfect. Oh, well, welcome, Andrew and Tracy. Yeah, having just come back from Japan, convenience stores are, really, really big. 7-Elevens, you can get anything you possibly want in a 7-Eleven. And people go in there to eat all the time. So all kinds of gourmet foods and stuff like that. So I think 7-Eleven's trying to do some of that in the United States as well. So um I think I'm on the right track there. No Casey's in California, I don't think. Um, so today we're going to look at the learning objectives under food chemistry. So the first one is to explain the chemical structure, properties, and interactions. So we're just going to focus today on the chemical structures and maybe a little on the properties, right? And then we're going to apply this information when we get to carbohydrates, lipids, and proteins, and many of the other things that we're going to talk about. So right now, in order to understand and explain the chemical structure, we have to learn just a little bit of chemistry. So, and then the other one is to understand major chemical and biological reactions that occur during food processing. So we'll take this information and we'll talk about oxidation and enzymatic browning and the Maillard reaction and pH and water activity and how the chemical structure is what drives those things. So that's what we're gonna cover today. So we're going to take this little bit of chemistry information that we have, because we're not going to cover all that today, and then we're going to apply it as we go through the class. So hopefully it'll make sense to you. By the way, just as a reminder, is no study guide for the exam. The learning objectives, the 2019 learning objectives are the study guide. So you should have a copy, and that's where this comes from, right? You should have a copy of the learning objectives so you know what they're asking. So they're not all that specific. So we have to use our imagination a little bit. So let's start out, first of all, talking about physical versus chemical properties, right? So the physical properties describe matter such as the boiling point or the melting point or the color. Those are physical properties. And so, and they don't require any change in the chemistry. So the chemical structure stays the same. So if we could think about that as water, for instance, right? The water molecule remains the same if we freeze it or boil it, or if it turns into steam, it's still the same water molecule. It still looks exactly the same. Chemical properties are characteristics that describe the chemical structure of the item. And so they are reactions that cause a chemical change, a change in the chemical structure. So maybe a little bit helpful. I ask you to learn a few definitions. So we have the atom, the element, a compound is two or more elements that are bonded together, and a mixture is two or more different substances that are not chemically combined. So it's kind of a nice little picture here. We have a compound, carbon and oxygen, while we have a mixture over here. It's got some nitrogen, oxygen, argon. It's got a mixture of different things, but they're not chemically bonded to each other. Any questions about those definitions? No, I think I asked you to do them in the homework. So last week we looked at the chemical structure. So we looked at the chemical structure of an atom. We said that the protons and neutrons are in the center of the atom, and that there are the same number of protons as electrons, and for our purposes as neutrons. When you get into those radioactive things, it changes a little bit, but in our world, they're the same. right? So if I look at the periodic table, I think I have one down here or not. There it is. If I look at the periodic table and it gives me the atomic number, that also tells me how many protons and how many electrons. And since neutrons don't have any charge, we don't worry about that, right? So then the electrons, which are the same number as the number of protons, circle the nucleus, the center part, in what we call shells. They're not actually shells, they're kind of doing this all thingy, but for us, they're shells. So that there can only be 2 electrons in the first shell. There can be up to 8 electrons in the second shell, and either 8 or 18 in the third shell. So what happens is, so it fills up the first shell, then, so this is argon, so we have 18. So we have 2 in the first shell, and then we fill up the second shell, that's 8. So now we have 10. So now we're going to have 8 in the outer shell, right? And that would be complete. And that argon is what's called a noble gas, and it doesn't react with anything because it has an outer shell of 8 electrons and that makes it complete. Questions about electrons and shells? And does this make sense?
Yeah, clear now. Thank you.
Okay. So if we look at the shells are labeled and their names are, and we don't really care, but they're KLM are the names. And just like I said before, there can be only 2 electrons in the first shell, 8 in the second, and either 18 or 8 in the third shell. So that's how they're always arranged. So the atomic weight is the weight of the protons and neutrons. It actually includes the electrons, but when we look at the atomic weight, the electrons are some little tiny fraction of the weight, right? They're little tiny because they're very, 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 very small. The atomic number is the number of protons. And the valence electrons is the number of electrons in the outer shell. And this is where all the activity occurs. All the activity occurs in the outer shell. So it has to do with the valence electrons. How many electrons are in the outer shell and how many empty spaces are in the outer shell. So if we look at nitrogen has an atomic number of 7. It has 7 protons, 7 neutrons, 7 electrons. So it's going to have 2 in the first shell and 5 valence electrons in the second shell. Right? I see Brian is nodding. Yes. I don't see a lot of people, so anybody else? So all the action happens here. Questions so far? So here we have, get out your pen, right? So I didn't talk too much about this, but I bet from your homework you can guess. What is the electrical charge of a proton? Get out your pen, and put a little mark, you write about here somewhere. That's right. Perfect. All right, it's positive. Great. Excellent. Oh, good job, everybody. This is fun, huh? Okay. And how many protons are there in this nitrogen molecule? It has an atomic number of 7. Yes. Good work. Good work. All right. What is the electrical charge of a neutron? It's kind of a trick question, right? Oops, oops. Sorry, I'm going to have to. Oops, did I erase something I shouldn't? That's right, 0. The electrical charge of a neutron is 0, neutral. It has no charge, but it has weight, right? So it has weight, then that makes the atomic weight. And how many neutrons are there? That's right, there are 7. Oh, we've got this wired. Great. And what is the electrical charge of an electron? Negative, right? Negative, negative. Very good. Very good. Okay. And how many electrons are there? 7. Right. Yes. Oh, we're awesome. And how many electrons are in the first shell? 2. Very good. Very good. Very good. All righty. And how many electrons in the second shell? 5. All right. All right. So how many of valence electrons are there? 5. Very good. Very good. Okay. You all pass. You get an A, right? Good. All righty. Let's clean this up. Anybody have any questions? Looks like I should move on. It looks like everybody's got this figured out, right? Great work. Thank you very much, everybody. So just looking at the periodic table again, we know that the rows are the number of shells. So you can see that there's 2 electrons in the first shell, 1, 2, and there's 8 electrons in the second shell, 1, 2, 3, 4, 5, 6, 7, 8. And then there are 8 or 18. Oh, excuse me, 8. There's also, whoops. Don't get carried away here, Joe. There we go. There are 8 in the third shell. There are 8 or 18 in the fourth shell. I'm fired. Fired. So if it comes up to 8, like 1, 2, 3, 4, 5, 6, 7, 8, and then it'll say, oh, my outer shell is full. But if it has 9, 10, 11, 12, or whatever, then it's gonna have more spaces. Okay, that's the periodic tables. So, and this is the number of shells. The rows are the number of shells, and the columns are the number of electrons. So I could say that potassium, right, is the atomic number is 19. So that means it's 2, 8, 8, and 1. And over here, sodium, let's pick an easy one for Pete's sakes, Jill. Don't work so hard at this. Chlorine is 17. It's going to be 2, 8, and 7. Yeah, think about that for a while. Most of you did really good on the chart, so I'm not going to go over it, but here's the answers to the chart. And you can compare that to yours. You do need to know the chemical symbols for these atoms, right? Most of them are pretty easy. Hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur. Sodium is Na, it stands for neutremia, and chlorine. So be sure you know those. Okay, let's talk about something now that I think we have that mastered. So that's any questions so far? No? Cool. All right. So let's talk about how the atoms interact with each other, right? How do they interact with each other? If there is a sharing of electrons, if they share the electrons, right, in their outer shell, it's a covalent bond. And these are the strongest bonds and ones that we can't break during cooking. So in other words, if we look at this methyl group right here, it's a carbon in the center with 4 hydrogens, right? And that gives us 1, 2, 3, 4, 5, 6, 7, 8 electrons. And so what the carbon does is, because the carbon is bigger than hydrogen, it kind of steals this electron, and the electron tends to stay closer to the carbon. So what happens is these electrons kind of go like this, kind of go like that, each one of them. So they kind of share back and forth and back and forth and back and forth. But so this is a, oops. Oh, all right. Do it that way. So this is these are covalent bonds, equal sharing of electrons. These are the strongest of the bonds, the strongest of the bonds, covalent bonds. These we can't affect by cooking. It takes really, really high heat to break this up. So these are the strongest. So if we look at carbohydrates, lipids, proteins, if we look at the structures of those, the carbons and hydrogens and oxygens and nitrogens are all covalently bonded to each other, right? So they don't, the hydrogen doesn't take a walk, right? It doesn't disappear. It stays. These are the strongest of the bonds, the ones we see. But sometimes there's interaction between molecules. Okay, so there's an interaction between. So if we look at water, these, you recognize these guys, right? H2O, these are water. And this, by the way, only happens with oxygen and nitrogen, right? So oxygen is really big. If we look up here at oxygen, we see oxygen is right there. It has an atomic number of 8. Hydrogen has an atomic number of 1. So, and that means it has 1 electron in its outer shell. So if this has 8, right, it's 2, 6, 7, 8. So it's missing 2 electrons in its outer shell. So what happens is it pairs up with these hydrogens, and these are covalent bonds, these ones right here, covalent bonds, strong bonds. But because the oxygen is big and the hydrogen is little, the electron tends to stay over here with the big family, and it leaves only the proton. And what did we say the electrical charge of a proton is?
Positive.
Positive, right. So that means that this side of the molecule is going to be positive because it's only the proton. The electron doesn't visit very often, doesn't like that family. It's too small, right? But now the oxygen has 2 extra electrons. And what was the electrical charge of the oxygen? I mean, of that question did not make any sense. Let's try it this way. Negative, right, because it's going to have 2 extra electrons. So this side of the molecule is going to be negative, and this side of the water molecule is going to be positive. So it's going to react with other water molecules that have the same structure, right? And so they're going to all kind of react with each other. The positive and the negative sides is going together, the positive and negative sides. And this bond between them right here, that bond between them is a hydrogen bond. It's called a hydrogen bond because it's hydrogen, the hydrogen and oxygen. Now this is a weak bond, so we could break it. So if we have water and we boil it, we add enough energy that the molecules start going really, really, really fast. Some of them can escape into the air. So we can break this bond because this is a weak bond. But this bond is what gives water all its wonderful special properties. Like, for instance, when you drop a drop of water on the counter, right? When you drop a drop of water, does it go all over the place? No, it stays in a nice little drop. So the reason it stays in a little drop is because of these hydrogen bonds. And the reason that you have to add so much energy to make water boil is because of these energy bonds. And the reason that you can float a bug or a pin on top of water is because of these energy bonds attracting to each other. And so these hydrogen bonds are what gives water all its special properties. Questions? No? Gone to sleep yet? No? So what properties of water can we think of? Right? What properties of water could we think of?
Could you describe one example so I kind of understand a little bit more about what you mean by properties?
Oh, okay. So properties like boiling, freezing, physical properties. Physical properties, the boiling, freezing, water activity.
Mhm.
Right? Those would be physical properties of water.
What about evaporation?
Mhm.
Evaporation, right? Okay, evaporation is a physical product where the water molecule, if there's a difference in the humidity between the water and the air, they can slowly escape into the air, right? So, because what we want is it to all to be exactly the same. We could think too about, when you think about cheese and crackers, right? And they put them in those cute little packages, right?
Mhm.
The water activity is significantly different between the cheese and the crackers. And if they were all in one package, they would all be the same neutral kind of rubbery, right? The
Mhm.
cheese would get rubbery and the cracker would get soggy because the water activity, the water would go back and forth between the two.
Is water activity the same as moisture migration?
No,
Okay.
no. Well, water activity actually probably I misspoke, but that's for moisture migration. You're right. Water activity, it has to do with the microbiology, right? But how other things can interact with the available water, not the total water, the available water.
Got it.
Uh-huh. Caught me. Um, Anyway, so this is an electrical attraction between the two. So this is a weak bond. When we think about freezing, so when water freezes, it expands, it gets lighter and floats, right? Because in freezing, these guys all line up and make crystals. So freezing interferes with this a little bit. Okay, so that's a hydrogen bond. So now we've done two different bonds. Covalent bond is the strongest bond that we can't break by cooking. A hydrogen bond, just think about water. Only think of hydrogen bonds, only think about water, right? Doesn't occur in many other places. The last kind of bond is an ionic bond. So if you put sodium and chloride in solution, one will give up an electron, and so it'll be slightly negative, and the other one will take it, and it'll be slightly positive, and the other one will take it, and it'll be slightly negative. And so then these two will react with each other, and these are called ionic bonds. So if we look at sodium chloride, we can see that sodium, right, has only one electron in its outer shell, right there. Only one. But if we look at chlorine, we can see that it has seven. 1, 2, 3, 4, 5, 6, 7. So it is missing an electron. This one right here. So what happens when we put it in solution is atoms are most happy when their outer shell is full. So sodium says, oh, you can have one of my electrons. So consequently, it gives up an electron and it becomes somewhat positive. And chlorine says, great, I'll take it. And so now sodium has 8 electrons in its outer shell, and chlorine has 8 in its outer shell, but now it has an extra one, so it's kind of negative. So what we have then are, well, these are what is called ions. That's their name, ion. So what happens when we put them in water, and the chlorine attracts the, because we said it's slightly yes, slightly negative. The chlorine is slightly negative. These pictures are drawn backwards. So that's what you get when you steal from the internet. So the chlorine is slightly negative. So the positive sides of the water molecule are attracted to it because it's slightly negative. And the sodium is slightly positive. So the negative side of the water molecule is attracted to it. So if you change the sodium chloride or the salt content of your food, it will also change the water activity of your food because of this ionic chemical reaction, this reaction. And these are called ionic bonds, and they're weak. They're really weak, but they're between ions, or things that are that there's a difference in the number of protons and electrons. Questions? Daniel, you have a question?
No, I'm not sure that
Not getting it?
I'm not sure that I'm entirely getting it in application. I understand that an ionic bond is where one um, atom shares an electron with another, which causes them to bond. I don't necessarily understand. Does that create a compound? Is that the phrase?
They are a compound when they're dry, right? When the
Okay.
two of them are hooked together, they are a
Yeah.
compound. But when we
Okay.
put them in solution,
With
they
water.
separate,
Okay.
right? And then you have ions. Thank
Okay.
you, Daniel. That's really good discussion, right? So they separate and then you have ions because there's an unequal number of protons and electrons.
Okay.
They have a charge, they have electrical charge,
Hmm.
right? So that something with an electrical charge because of an uneven number of protons and electrons. That was good clarification. I like that. Anybody else?
I have a quick question. The when the electro the when the s- so the sodium and chlorine when it takes that now it loses that third outer shell. It loses it. It just goes away and goes to chlorine or chloride. I'm sorry. Is that what I'm seeing? Is that what I?
Yeah, what you're seeing is that the electron over here, this
Yep.
electron over here, is going over here to
Yep.
chlorine.
And
Yes.
then that outer shell goes away because there's no more
There's nothing there.
electron. Okay. I
The
see
shell,
it, but I just want to clarify it. I
oh,
want to make
thank
sure
you.
it's not like invisible or some kind of
No,
I
it's
don't
not
know.
there.
Okay. Okay.
The shell part
The shell is what I
is
meant to say. The
it's
shell is
just
gone. Yep.
the
Okay.
shell is just where they rotate, but it's not a physical thing like a racetrack.
Okay. And can it pick up another shell somehow?
Uh
Or is that
No, no, it cannot. So, all it's going to do is fill up or give up. What's
okay.
the sodium is giving up this electron because it's the only one out there, right? And it's
Hmm.
long ways from the nucleus.
Yep.
So it's only weakly attached. So, and the chlorine is bigger, right? It's bigger.
Hmm.
So the chlorine just grabs it up.
Okay.
And then the chlorine says, oh, yay, now I'm happy because now I have 8 electrons in my outer shell.
Yep. Okay.
Yeah,
That
yeah,
makes sense. Okay.
And
yeah.
I guess I do have a question, Joe. In this application, so when salt is a compound, it encounters water activity or something that contains water and it is dissolved, which then becomes a electrically charged ion. What does that do to flavor, right? Because I think that's, sitting here with a few other chefs. Is that when I'm assuming that's the difference between putting dry salt on my palate and it creating a kind of one-dimensional, very pronounced saltiness versus a like distributed salinity. I think I'm just trying to
Uh,
understand this in context.
well, we can't taste anything unless it's in solution. So we can't
Uh-huh.
taste dry things.
Got it.
So when you put that dry salt on your tongue,
Uh-huh.
you can't taste it until it dissolves,
That
right?
helps this make so much sense.
That makes sense.
Which
Okay.
is what, yeah, that's cool.
Right.
Which
Yeah,
is why saliva is such a critical thing, I
right. And
suppose, right?
yeah, people who have on medications and stuff who have a dry mouth,
Uh-huh.
they
Uh-huh.
can't taste as well. Right. It has to be in solution
Wow.
for it to be the taste buds, so the taste buds will recognize it. Right. So
Wow, that's cool. Okay, thank you.
yeah. Okay. And we're going to talk about this a lot more, but this is these are ionic bonds, and these are particularly important when we talk about water activity later on. And when we reformulate, you know, the FDA is big on getting us to reformulate to uh, you know, to lower the salt in foods. And it's always very important that we recognize that it's going to affect the water activity. And if the water activity gets too high, it could affect the microbial, you know, the pathogens and the microbial and food safety issues. So that's how that works. Great, great, very good. Thank you guys for those good questions. That was very good. So finally, then we would talk a little bit about functional groups. So it turns out that the whole molecule, a lot of it's just there to hold on to the little bits that are around the outside that actually do all the action that are the functional groups. So the functional groups are the reactive groups. So if we look at this whole model, let's say um, a fatty acid, for instance. So we look at it carbon, 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 carbon. And at the end, we see a carbon, two oxygens, and a hydrogen. This part of the molecule, it just stays the same. But this is the functional group, and this is the part of the molecule that reacts, right? So reacts and bonds and makes the triglyceride and all of that sort of stuff. So anyway, so the functional group is where the action takes place. Sometimes in these things, you're going to see a thing that's called an R. It's a radical. And the R just stands for the rest of the non-functioning molecule. This other part over there that we're not worried about. So we're just only looking at the little bitty bits that actually react. So here's my fatty acid again. So this group down here is called a methyl group. It is a non-reactive. Carbon can bond with four things in its outer shell. So this is non-reactive. So this is a methyl group. But the acid group that I was showing around here before, this is carbolic acid. This is the reactive end. All the rest of this is the fatty acid chain, and it is not reactive. So, but the first group here we're talking about is a methyl group, CH3, carbon, carbon, hydrogen, hydrogen, hydrogen. So it's non-reactive. So the more methyl groups you have, the more non-reactive your compound is going to be. Another group is the hydroxyl group, which is an OH. An OH, it looks like this. Here we have a compound is 2 carbons, 5 hydrogens, right? And then this OH group. If I was looking at it in this molecule, the oxygen is the red part. This is the OH down here. So we just got finished talking about water, right? H2O. So what happens with these OH groups is they like to split, and the hydrogen likes to go for a walkabout. So it goes, but it doesn't take its electron with it. So it goes for a walk. It's Australian. It goes on vacation. It goes for a walkabout, right? So this hydrogen likes to go for a walkabout. So anything that has lots of OH groups in it is going to react with water because it's going to be positive and it's going to react, you know, it's going to hydrogen bond with water. So things like sugars have a lot of OH groups. Some proteins have the water OH groups. So but if we look over here, we look at this fat right here, it has no hydroxyl groups, no OH groups. And what do we know about fat and water? What about fat and water? Do they
Doesn't
They
mix.
they
add,
do not mix,
they
right?
add, right.
And they do not mix because fat does not have any hydroxyl groups. We don't count this part down here. Does not have any hydroxyl group. But we look at sugar, sugar and water do mix because sugar has a lot of hydroxyl groups. Okay? So then looking here, a carbonyl group is a carbon and a double bond to an oxygen. And when we look at aldehydes, it's a carbon double bonded to an oxygen called the carbonyl group. And a ketone is also carbon double bonded to an oxygen. So they have carbonyl groups. So here I was talking, this is sugar. See all these OH groups right here? So that means that it's going to react with water because some of these hydrogens are going to go walkabout. So it's going to react with water because it's a lot of OH groups. This up here at the end, this is called an aldehyde. The OH is on the end. So some sugars, all sugars have the same chemical formula, C6H12O6. They all have the same formula, C6H12O6, but where the double bonds are and where the oxygen is changes from one sugar to the next. So the way they look changes. So if the double bond is on the end here, this is a aldehyde. It's called an aldehyde. And if the double bond is in the middle, it's called a ketone. And the memory aid is, somebody told me, ketones are in the middle of the chain. They do not like to be alone. Ketones and alone, right? So they like to be in the middle. Then when we talk about the Maillard reaction, we're going to talk about the fact that there are some sugars that they don't, like sucrose doesn't participate in the Maillard reaction. And so because it's a non-reactive sugar because it doesn't have the double bonds. Much later, we'll talk about that much later. So that's a ketone. So the sugars that do not have double bonds are called reducing sugars. And they do not participate in the Maillard reaction because they don't have any of this. This double bond right here is really weak. This much weaker than these. So the chemical reactions can occur.
And Joe, just to again, I'm a context guy. Sorry to take everybody else's time, but so sucrose is found a lot in like tropical fruits and citrus. Would that be why it's very difficult and nearly impossible to like dry caramelize a like one of these fruits because they do not participate in Maillard reaction because they just start to kind of dissolve or break down instead of caramelize?
You're mixing up two different terms. So Maillard reaction is a reaction between a sugar and a protein. So there wouldn't be a Maillard reaction because there'd be very little protein in the sugar. Now, caramelization is different, and caramelization is a browning based on heat. Like if you made caramels, right? When you cook the caramel and you cook the sugar, and it gets darker and darker, that's caramelization.
Mhm.
So you just might need more heat. I'm not sure
Mm.
about tropical fruits. Maybe somebody else on the call can say, but I'm talking here about the Maillard reaction. Was a reaction
Mhm.
between a sugar and a
And the
protein.
protein. Got it.
Right, right. Now you may say, well, there's lots of sucrose in things and they brown. And yes, they do because the sucrose will disassociate. And when it disassociates in water, then it would participate. But as sucrose itself is a non-reacting sugar.
Okay.
We'll talk about that more.
Yeah, that's cool.
Yeah. We'll talk about that more for sure, for sure. Right? Okay. And then this one here, this is called carboxylic acid. I talked about that before, right? So this is COOH. Lots of times you'll see it written like this, COOH. And there's this double bond, this weak double bond right here, and an OH. And this is an acid. These are organic acids. All the organic acids have carboxylic acid groups. That's an acid. COOH. The organic acid, like vinegar and tartaric acid in grapes and stuff like that. Proteins have nitrogen in them, and this is called an amide. This is NH2. Sometimes you'll see nitrogen, it can be also NH3, but this is an amide, NH2, nitrogen. This is the backbone of a protein. This is what makes for the long chain. So every protein has an amino acid and a carboxylic acid and a radical meaning the rest of the molecule, which is different on each different amino acid. So that's an amide. So when we talk about proteins, we talk about what makes them different. And what makes them different is they have nitrogen, while carbohydrates and lipids do not. This is a disulfide band, brown. It just means it has sulfur in it, not so much. We don't worry about that. This is phosphate. So if you do anything with meat and you add phosphates to it, see all these OH groups right here, right? So all the chemical properties of phosphate, the water holding capacity increases because of the phosphate molecule. And you know, it could be phosphorus, phosphide, depending on how many electrons are there. That's phosphate. So we talk about that when we talk about marinades. So I put a little chart in here kind of to help you out, give you the down and dirty parts, right? So look at that. Again, how are molecules drawn? I just want to spend a little time on this because we are almost out of time. But all of these are exactly the same thing. These are all glucose, C6H12O6. This one's pretty easy because you can see here's all your carbons in a row and you can count all the hydrogens and oxygens. But in reality, in the world of liquids and things like that, the sugars don't go around in straight lines. They like to form a cyclic compound. This is exactly the same thing. Sometimes we'll see things drawn without the carbons. So at every one of these corners is a carbon. They just didn't bother to draw them in there because it gets too complicated. And this particular one, these dashed and dark lines mean that because these things are not flat, they're three-dimensional. So these dashed and dark lines, I think the dashed means it's going to the back, and the dark means that the oxide is coming out of the front side. So if you look at this right here. But these are all exactly the same thing. They're just drawn in different ways to be confusing. Okay. But when you see them, and I'll be using them in class, pretty much if not all the carbons are drawn, it's all kind of the same. They're all the same thing. And finally, the ending of class, we do not have to balance equations in this class. Yes, that's wonderful. But in essence, what happens is that when two things combine, they don't add or lose atoms. There's the same number on both sides. So they just change partners. It's a little bit like musical chairs. So when you get done, there's still only one carbon, 4 hydrogens, and 4 oxygen. But both sides of these are equal. But you can see that we went from a methyl plus two O2s or 4 oxygens to carbon dioxide and 2 waters. So it's just that chemical reaction. But we don't have to balance equations. So this side over here, this side is called the product. And the other side is called excuse me, this is the reactants. And this is the product, in case you care. We don't care. All right. Are you baffled? If there's something of this that you want me to cover again next week, let me know. Oh, dude, there was somebody in the chat a long time ago. Oh, somebody likes Coldplay. So yeah, so if there's anything that you want me to cover again, next week we're going to talk about carbohydrates. So we'll be looking at where to go. These guys, these are sugars. This is carbohydrate. Any questions? Okay.